This section explains why deep learning works at all, and the single idea that unifies its architectures. Generic high-dimensional learning is cursed. Real tasks escape the curse because the physical world hands you regularities for free, and those regularities are symmetries. One move generates the whole field. Fix the symmetry group of your data domain, the translations of a grid, the permutations of a graph, the rotations of a sphere. Then demand that your architecture be invariant or equivariant to it. That single constraint is the architecture. Convolutional networks, recurrent networks, graph neural networks, and transformers stop being separate inventions and become instances of one blueprint. This is the Erlangen program transplanted. Klein defined a geometry by its group of symmetries, and here a network class is defined the same way. Symmetry as prior knowledge, character, minimized into structure. This part explains why one idea, symmetry as a constraint, collapses the hardest problem in machine learning into something solvable. Generic function estimation in high dimension is hopeless. This is the curse of dimensionality. The escape is that real tasks carry structure. They inherit the symmetries of the physical world. A shifted image is the same image. A rotated molecule is the same molecule. Impose that symmetry group as a constraint on the function class, and the search collapses to something learnable. That single move, invariance under a group as an inductive bias, is the whole thesis. Under it, CNNs, RNNs, GNNs, and transformers stop being four architectures and become one blueprint read through four groups. This is Klein's Erlangen program, where a geometry is its symmetry group transplanted onto deep learning. The generative primitive is this: name the symmetry, derive the architecture. This section lays out why learning in high dimensions is hard and what that hardness actually tells you. Learning is choosing from a rich enough class the function that fits the data while minimizing some complexity measure. The most regular interpolant wins. The chapter's whole work is to show that generic regularity buys nothing in high dimension. Ask only that the target be Lipschitz, and pinning it down demands an epsilon net of the domain, on the order of epsilon raised to the negative d samples, exponential in d, more than the atoms in the universe at modest dimension. Sobolev smoothness rescues nothing unless the smoothness order scales with d, which never holds. So the curse is a verdict, a final answer, rather than a bound to be tightened. The prior must come from where the data lives, not from smoothness alone. That is exactly the opening the geometric priors of the next chapter fill. This section explains why learning needs regularity and why plain smoothness is not enough to supply it. Learning is a search for the most regular function consistent with the data. Regularity is the only thing that lets finitely many samples pin down an infinite object. The chapter's whole force is that generic regularity buys you nothing in high dimension. Ask only that F be Lipschitz or Sobolev, smoothness is too weak a prior. On the number of samples needed to nail it grows as epsilon to the minus d power. That is the size of an epsilon net of the domain, exponential in the dimension d. On it passes the atom count of the universe for even a modest d. Once volume explodes, smoothness is too weak a prior. The primitive to carry is this: a usable prior must come from the structure of the domain itself, rather than from unstructured smoothness. That is precisely the gap geometry is built to fill. This part explains the two geometric priors that make high-dimensional learning tractable. What rescues high-dimensional learning is not more data. It is the observation that real signals live on a structured domain, call it omega, and the function you seek respects that structure. Two priors do all the work. The first is symmetry. The target is invariant under a group acting on omega. Shifts leave an image's class untouched. Rotations leave a molecule's energy untouched. So the hypothesis space collapses to group equivariant maps. The second is scale separation. Coarsening omega preserves what matters, so interactions factor across scales. Together, these two priors defeat the curse of dimensionality that Chapter 2 diagnosed. The convolutional neural network is both priors at once. Weight-shared convolution is translation symmetry. Pooling is scale separation. Everything later, graphs and manifolds, is this same pair transplanted onto a new omega. This section explains geometric deep learning as the escape from the curse of dimensionality. The curse of dimensionality, established in Section 2, proved that generic high-dimensional learning is impossible. Approximating an arbitrary Lipschitz function needs a number of samples that grows exponentially in the dimension d. That exponential wall is what any real learner must somehow get around. Geometric priors are the escape, and they are the whole book's thesis in miniature. Physically structured data is never generic, so the move is to restrict the hypothesis class to functions that respect the domain structure. Two principles do all the work. The first is symmetry, invariance or equivariance under a group acting on the domain. Omega, the second is scale separation, meaning survives coarsening the domain. Every successful architecture is one instance of exploiting these two principles. Convolutional networks, graph networks, and transformers are all the same idea, worn differently. Here is the generative move. Do not ask what a network computes. Ask instead what group it is blind to. The symmetry itself is the inductive bias that beats dimensionality. This section explains how 5 geometric domains collapse into a single move. Grids, groups, graphs, geodesics, and gauges are 5 domains fed through one blueprint. A signal lives on some space, call it omega, and the admissible operations are exactly those that commute with omega's symmetry group. Fix the group, and the network follows. Graphs carry the permutation group sigma n. Grids are graphs with translation added, so they are a special case rather than a separate species, which is why the ordering here is pedagogical rather than by generality. Geodesics supply metric structure on manifolds, and gauges supply the local frames on their tangent bundles. The generative primitive is that architecture is the invariance. Name a domain's symmetries, and you have already specified what its layers may compute. This section lays out the single move behind Chapter 4. There is one generative move dressed 5 times. Name the substrate, read off the group of transformations that must leave answers unchanged, and the rest of the machinery is fixed. Chapter 4 enumerates the substrates, grids, groups, graphs, geodesics, and gauges. The thesis is that these are one theory seen from 5 points in a single parametrization, the triple of domain omega, signal space, and symmetry group. Graphs give the permutation group sigma n. Grids are graphs with extra structure, so their symmetry is a subgroup. The ordering is pedagogical rather than by generality, grids sitting inside graphs, chosen so each group G lights a facet, the others do not. Learn to extract the group from the domain, and the 6th substrate explains itself. This section explains why 5 deep learning architectures are the same operator, wearing different symmetry groups. Every architecture you already know is the same operator wearing different symmetry groups. Fix a domain, name the group that must leave it invariant, demand equivariance plus locality, and the layer is no longer designed. It is forced. Translations on a grid collapse to the convolutional neural network. Permutations on a set give deep sets and, with attention, the transformer. A general graph's automorphisms give the graph neural network. Gauge symmetry on a mesh gives intrinsic mesh convolutional networks. Time warp stability on a temporal grid gives the gated recurrent networks. Time warp stability on a temporal grid gives the gated recurrent network. The primitive to keep an architecture is a choice of symmetry. So any future model is placed by asking what it refuses to change. This section shows how the whole zoo of neural network architectures collapses to a single generator. Fix 3 things: a domain, a symmetry group, and a notion of locality. The blueprint from section 3.5 then emits an architecture as its unique local equivariant solution. Convolutional networks come from grids under translation. Group convolutional networks come from adding rotations. Graph neural networks come from adding rotations. Graph neural networks come from permutation on graphs. And then deep sets, transformers, mesh convolutional networks, and gated recurrent networks each. The chapter is a demonstration that these were never separate inventions. They are coordinates in one space. The generative payoff is this: to place any future architecture, read off its invariances, and locate it by domain, group, and locality. No new theory needed. This section explains why the book's closing chapter treats the era's celebrated successes as instances of one idea. The 5 geometric domains were never invented. They were found sitting under the data that physics and biology already produce. So this closing chapter reads backward. 1 blueprint, retrodicting what already worked. 1B, 1 blueprint. 1B era's celebrated successes turn out to be geometric deep learning instances whose authors mostly never used the name. AlphaFold, folding proteins over contact graphs. A graph neural network discovering halicin. Drug repositioning cast. The chapter's function in the book's arc is vindication by unification, proof that symmetry-first modeling is a recognition of structure. The world hands you, not a stylistic preference. Predict the next instance by asking only where the symmetry lives, and the architecture follows. This section explains how the 6th chapter closes the book by turning its own method around. Every earlier chapter derived an architecture from a symmetry. Here, the symmetry is read back off the world. Real data arrives already carrying invariances, so the 5 geometric domains, grids, groups, graphs, geodesics, and gauges are the actual shapes the problems already have. Molecules are graphs. Proteins are structures in space. The century's famous machine learning successes, drug discovery, protein folding, recommendation, come out as byproducts of that geometry, often found without the builders naming it. The chapter proves the blueprint by pointing. Wherever a real problem has structure, one of the 5 domains is already waiting inside it. This section places geometric deep learning inside one recurring pattern. A discipline matures the moment it stops cataloging its objects and instead names the group of symmetries that generate them. Klein made this move for geometry in his Erlangen program. declaring symmetry the organizing principle of the whole field. Noether made it for physics, proving that every continuous symmetry yields a conservation law. The chapter's work is to show that geometric deep learning is the same move, arriving late to machine learning. Invariance and equivariance are the symmetry principle itself, already ancient in geometry and in physics, finally installed as the foundation of learning. This section places geometric deep learning at the end of one long lineage. The generative pattern is simple. Whenever a field matures, its invariances get named as a group, and that group becomes the organizing principle for everything built on top of it. Klein made this explicit for geometry in the Erlangen program. Noether turned it into physics, deriving conservation laws from continuous symmetries. Machine learning rediscovered the same move, piecemeal, from Fukushima's shift-invariant neocognitron through convolutional networks to graph networks that arrived independently from chemistry, network science, and recurrent structure processing. Read this way. Geometric deep learning is the Erlangen move applied once more, and you can predict each earlier instance from the pattern itself.